In this video, we introduce an innovative approach called StriderNET. StriderNET is a graph reinforcement learning algorithm for the optimization of atomic structures on rough energy landscapes. Optimization of atomic structures has several important applications such as discovering new materials, optimizing materials for targeted mechanical properties, and drug design. Let us first look at the idea of energy landscape. The energy landscape is a continuous mapping from configuration space to energy space. An n-atom system has a 3n-dimensional energy surface. And studies have shown that glass-forming amorphous systems have a large number of local minimas that increases exponentially with the number of atoms. Thus, it is challenging to find low-energy stable configuration in such rough landscapes. Simple optimization methods that follow the energy gradient usually get stuck in high-energy local minima. StriderNET, being reinforcement learning based, explores the energy landscape and thus discovers lower energy stable configurations. Let us now have a look at the architecture of the model. First, the initial configuration of the atomic system at step t equals 0 is transformed into a graph representation by providing the node and edge features. Next, using a message-passing graph neural network node and edge embeddings are generated. The generated embeddings are passed through a multi-layer perceptron, which predicts mean displacement for each node. A multivariate Gaussian distribution is then employed to model the probability distribution over the continuous action space. Actions are sampled using the predicted mean value of displacements and a fixed standard deviation, which is a hyperparameter. The nodes are now displaced to get the updated graph, and the corresponding change in the system's energy is used to calculate the reward. This process is repeated for t steps to generate a trajectory of optimization. Finally, using the obtained discounted rewards, the policy loss is computed and parameters of the policy updated. Using the proposed methodology, we test our approach on 3 different atomic systems. First is the binary Lennard-Jones system, which is a well-known model glass former having a large number of local minimas. Second is the Stillinger-Weber silicon system. It consists of complex 3-body angular interactions, making optimizing more challenging. The third system is a coarse-grained model of cement hydrate gel. The interaction in this system is similar to Lennard-Jones system but of a higher degree polynomial. All these systems exhibit a rough energy landscape. The following curves show the rewards as a function of training epochs. We see that as the training proceeds, the model receives higher and higher rewards for all 3 systems. For validation, we also calculate the average reduction in energy over an optimization trajectory of 20 steps. We again observe that as the training proceeds, the model optimizes the system better and better. Once we obtain the trained model, we adapt it to a target structure which was unseen during training. Toward this, we optimize the parameters as well as the target graph using the previous mentioned approach. The central idea is to keep optimizing the target structure for an extremely long trajectory much larger than the training trajectory. This leads to improved performance, and the model outperforms several classical optimization algorithms like gradient descent, atom, and fire. The following curves show the performance in terms of energy of the system in comparison to the baseline methods. It reaches lower energies both in terms of mean as well as minimum over 10 different structures. Next, to analyze the inductive power, we tested a model trained on a 100-atom system on systems of size up to 1,000 atoms. We observed that the model outperforms the baseline methods up to an order of magnitude larger system than it was trained for. To evaluate the importance of each node and edge feature, we perform a feature ablation study by training the model with one of the features removed at a time, and computing the average reduction in energy over 20 optimization steps. We observe that without the edge features, the performance is significantly reduced. And although the model performs quite well even without energy-based node features, its performance is enhanced by using them. Thank you for your kind attention. For further in-depth discussions, we invite you to our poster booth number 544 in Exhibit Hall 1 on Wednesday, 26th of July, at 11 a.m. We also encourage you to read the paper and check out the freely available codes by scanning the QR shown or using the links provided. Thank you.